let's take a look at a E2 mechanism. E standing for elimination, 2 standing for bimolecular. So a general a reaction scheme of this, let's say we have ourselves a base, and then we also need to have the substrate. So let's draw ourselves a substrate here. And there's our leaving group. Notice that you have a leaving group attached to a carbon, and then attached to this carbon that I'm pointing to is another carbon that has a hydrogen. All right. So we could number it if we'd like. We could say, hey, this carbon we could say is the alpha. That marker doesn't work anymore. Let's see here. We could call that one alpha. And this would be the beta carbon. So we need a hydrogen on the beta carbon. Because what's going to happen mechanistically is the base and the leaving group, and watch this, we'll just draw it here. So the base comes and does what bases do. They abstract the proton. The 2 electrons in this hydrogen-carbon bond are going to then come and be donated in between the alpha and the beta, and then that's going to kick off the leaving group. See how there's 3 mechanistic arrows in this mechanism? And so what's that going to give us? We're going to have our carbon with those 2 methyls double bonded to this carbon with its 2 methyls plus our leaving group that is going to be negatively charged. Now we can contrast this to an E1. So in E1, we could have the same molecule, but the mechanism proceeds a little bit differently. What's the first step? The leaving group leaves, generating a carbocation. And then our base can come in and abstract that proton to give us our product, like so. Now you're probably looking at that and say, well, get the same product, why does it matter? Well, we will answer that question in a minute. Before we get to answering that question, let's just look at the energy diagram of the E2 and what that's going to look like. So if we draw ourselves an energy diagram, this is our reaction coordinate. Okay. This is our potential energy. So remember what the 2 means, bimolecular. So that means in the transition state, there's going to be 2 molecules coming together. Okay. And so what do we have here? This is going to be our starting material right here. So that starting material includes the substrate. Okay. And so it's going to go into a high energy state and then go to a lower energy state. And there's going to be our products. Okay. Extend that x-axis over there. And so what's happening at the transition state right here? Well, we have the base that's starting to form the bond with the hydrogen. And the leaving group is starting to leave. And what else is happening? This bond right here, hydrogen-carbon bond, is also starting to break. And what bond is starting to form? That one, the double bond. Because remember what the product looks like. Looks like this. And so when And so this one starts out full-blown negative, so that's going to be a partial negative right there. And then this one's going to leave, and that's going to become a negatively charged, so that's going to be partially negative right there. And then what's on the product side as well? The base has abstracted the proton, so that's going to be BH, like so. So what's happening in the transition state? Well, we have this molecule and this molecule right there. So bimolecular. Two molecules are coming together in the transition state, but to be more specific, in the rate determining step. But there's only one rate determining step in an E2. Okay. So that's what the energy diagram looks like. Okay. And I would highly recommend contrasting the E2 energy diagram to the E1, and you'll see the difference there as well. So let's go back to that question I proposed at the relative beginning of the video. With an E2 and an E1, you got the same product in this example. So why does it matter? Well, when the molecules are not in this general scheme, we're going to see something really interesting about this. So here's the answer. If we invoke a E1 mechanism, so let's use ethoxide, okay, as our base in this particular example. What you're going to get is two products. You're going to get a product that looks like this. Let's see, we can have the two phenyl groups on the same side, like so. Now let's draw the hydrogens, because we need to be clear that that's forming a bond with the carbon there, like that. So it could have this product and this product. Like that. Both of those would be formed. This one would be the major product. This would be the minor. And the reason why is this one would have less sterics, because here we have those two phenyl groups on the same side, which will cause some steric clash and be higher in energy. So this one would be the major product. Contrast that, though, if we take that same molecule, okay, and we take that same molecule, but we invoke the E2 mechanism. So let's make sure I have this written as our E1. Oh, it's already right in there. Okay. Let's do an E2. Okay. So we'll start with the same molecule. Like this. And what else? We need our methyl. Like that. Now, if we invoke an E2 mechanism, notice what's going to be different about this. Now, we could use ethoxide again if we'd like. So we would anticipate that we would get two products. But, in fact, we only get one. And the one that we get is this one. Right? Like that. Only one. This is the only product. We don't get a mixture. So that is a huge difference right there. Two products versus just one. Okay? And so an E2 reaction can be stereospecific. You're only going to get one stereoisomer. Now, why is this the case? Well, the word that you need to remember is this word right here. Anti-periplanar. What that means is that the hydrogen that's being abstracted, that's attached to the beta carbon, so this carbon's our alpha because that's directly attached to our leaving group, so that makes that guy beta. And I'm going to take this phenyl group and just push it down a little bit so you can see it a little bit better here. Like this. Still on the screen? Good. What's not drawn here is the hydrogen that's going to be abstracted until now. I'm going to draw it. Okay. So, this periplanar thing right here, okay? What that's looking at is that the hydrogen and the leaving group have to be in the same plane. Do you see how the hydrogen-carbon bond is just a line, and then the leaving group that's attached to the carbon is just a line? That's implying that it's in the same plane. And so that's that part, okay? It has to be in the plane. Now the other part here, this anti, when you take a look at the beta and alpha carbon, do you see how it's oriented in space where the hydrogen is on the top face and the leaving group is on the bottom face? They're on opposite faces of this beta-alpha bond right here. And that's what the anti part means. In order to do a E2 reaction, the hydrogen and the leaving group have to be anti-periplanar to one another in order for it to work. Whereas when you take a look at an E1 mechanism, it doesn't matter if the hydrogen and the leaving group are anti-periplanar. Why? Because what's the first step in an E1 mechanism? The leaving group leaves, and you generate a carbocation. Okay? So let's take a look at this a little bit more closely. So I'm going to erase this board now. So let's take a look at this problem a little bit more closely here. And I want to show you and teach you how to predict. If this is what you were given, and you said or told that it's going to do an E2 mechanism, and so we have our ethoxide here. How are you able to look at this and then predict the product over here? Okay? That's what I want to show you here. So also realize that there is a dashed hydrogen coming off of there. Okay? Recall, we do not take off the hydrogen that's attached to the alpha carbon. It has to be the hydrogen on the beta. And in an E2 mechanism, what has to happen? The hydrogen and the leaving group have to be on opposite sides of the alpha beta, and they have to be in the same plane. So when our base comes in, what does the mechanism say? It's going to grab that proton. It's going to take the two electrons in that hydrogen-carbon bond and put them between the alpha and the beta. And then the leaving group is going to be kicked off. And so this is what I suggest to do. Draw the two carbons. Okay? You could draw them like this if you want, or just draw two carbons like that. This is the way I probably get used to doing. Okay? Now, just leave these groups as they are. Okay? Just leave them as they are. And so what's happening here is our CH3 is like this, and our phenyl group is like that. You see those? I'm keeping dashed and wedged, right? And so I see a dashed hydrogen over there, and then a wedged phenyl group right there. Now this is an alkene with these groups pointing out at you and these groups pointing into the glass. So you could represent that like my hand flat like this. But I could take this molecule. Do you also see how my thumb's sticking out? I look at that as like the groups that are sticking out here. The methyl and the phenyls is my thumb. Okay? Now if I take my hand and rotate it 90 degrees and put it flat, what do I see? Well, this piece right here can also be represented like this. Okay? Phenyl, H, phenyl, and our methyl. Both representations work. But the important thing to see here, this is dashed, that's wedged. So that means they're on the opposite sides. And so when you take that molecule, this molecule that looks like this, and rotate it 90 degrees, you get something that looks like that. And once again, you see that those groups are opposite, on opposite sides of the alkene. And that's how you view it. So let's do a test here to see if you truly understand what's going on. Okay, so let's do a practice problem. And I highly encourage you to pause the video after I write it down and see if you can solve it before you watch me give you the answer. Okay. So what if we had a compound that looked like this? Okay. There's our Br. Let's put a deuterium right there. Dashed hydrogen. Our methyl. Hydrogen like so, and another methyl. Nice, all on the board. Okay, perfect. So D is just an isotope of hydrogen. So you can treat this D and that hydrogen the same. Okay. So the question is, we have our alpha. There's our leaving group, and so that makes that guy the beta. And on the beta, we have a deuterium and a hydrogen. When we treat that with, let's say, ethoxide, right, and we're invoking an E2 mechanism, which hydrogen, or the deuterium or the hydrogen, which one's going to be abstracted? And so it can abstract the deuterium at this particular spot right here, because look, leaving group, a D, they're both in the same plane. They're both just the lines. And they're also anti from that alpha-beta bond right there. And so in this conformation, our ethoxide can come in and grab the deuterium like so and give us our product. And our product's going to look like what? We can just say, okay, our double bond. We see that the methyl here is a wedge, and this methyl is a dash. So that means they're going to be on opposite sides of one another, like this. And then on this carbon on the right, we have a hydrogen, and we have another hydrogen right there. All right? So we could get that product right there. Well, what's interesting about this particular example is that you have free bond rotation around the alpha and the beta. So you could take this molecule drawn in blue, and let's redraw it. Okay. I'm going to leave the right side of that molecule the same. But I'm going to take this piece right here and rotate it. Watch what happens when we rotate it. I can get the hydrogen like that, and then I'll have our dash and our wedge. Now, if I rotate this, where's my deuterium, and where is the methyl group going to go? Okay. Our deuterium will go there, and our methyl will go there, like that. Now we can invoke the same mechanism. It's going to be an E2. Remember, we are using electrons when we draw these mechanisms. So take that lone pair, grab that, go like this, and kick it off like that. Now what do we have? We have a carbon-carbon double bond. I see I have a methyl. I see another methyl, but that methyl is also a wedge, so that's going to be on the same side as that methyl. And then we have our deuterium, and then our hydrogen right there. So you see in this particular substrate here, we can get two products, okay? But we still have to invoke the anti-periplanar rule in order for that to work, okay? But in our previous example, there was only one hydrogen. Then in our previous problem, we only had one hydrogen on that beta carbon, so it could only give us one product. But in this particular case, we have two protons that can be abstracted. And so you rotate around that double bond, or rotate around that single bond to take a look at which hydrogens, or which hydrogens, deuterium and hydrogen, same thing, if you can get those into the anti-periplanar conformation. Okay. Let's take a look at why does the hydrogen have to be anti-periplanar. One way you could look at it is, let's take this group right here and rotate it in such a way that it looks like this. Okay. So we'll draw it exactly how we have it here, but when I rotate it, I now want the bromine, and so that would put the hydrogen there and a dashed methyl, like so. All right. So in this conformation, it does not work. The ethoxide does not come in and abstract that proton and break that off. So what I'm drawing now is 100% incorrect. Okay? That comes in, grabs, breaks. Okay? That's incorrect. Okay? Why is that incorrect? Well, what do you see is going on here? What's happening all on the same face of the molecule? It's the top face. We have something coming in, at the same time something's leaving, and it's just going to be a mess. But when you do an anti-periplanar, you have something coming in from the top face, you have something leaving from the bottom face, and that's how it works. It can't get too crowded. And so in an E2 mechanism, it has to follow this, anti-periplanar. Okay? And so that's one explanation as to why you need an anti-periplanar. Something that you need to be aware of is that sometimes you'll have a substrate, okay, where you could have, let's say, the leaving group, bromine, as a wedge. Then you have some hydrogens and a methyl group right here. Then we could have a CH3, a wedged hydrogen, and a dashed methyl, like so. Okay? And it says, we're going to invoke a E2 mechanism, predict the product. So what you have to do is to get this molecule right there in the proper orientation. Okay? So that requires us to do some rotating around the alpha-beta bond. So there's our alpha, there's our beta. So we have to rotate it to make it in the anti-periplanar conformation so we can figure out what our alkene is going to look like. So one way that I like to do it is draw Newman projections. All right. And these Newman projections help me to orient everything in its proper space. So if I take my eyeball right here, okay, and look down this bond here, I'm just worried about this front carbon right here. That front carbon, the way that it's drawn, I see that I have a methyl up top, like so, and then what? We have another methyl right there, and my hydrogen right there. Okay. That's what I'm seeing. What do I want? I want this hydrogen, which is that hydrogen, to be in the plane. And if I want it up here, I want the hydrogen to look like this. I want it in the plane, so I want to put it there. And in order to get it there, I would have to rotate this. And, let's change up the substituent so we can actually trace it. So we'll keep that a methyl. Let's turn that one into, let's say, an ethyl. Okay? So we can track this a little bit better. So if I rotate that, so now my ethyl is going to be here, and my methyl is going to be right there. All right? So I'm going to then start redrawing the molecule here. So if I want my hydrogen up, it's going to now look like this. When I rotate it, my hydrogen is now going to be up like so. And then what's going to happen here? My methyl there and my wedged ethyl there. All right? See that? Now, what do I want to have happen over here? I want that bromine right here to be underneath anti-periplanar. So I want that in the plane. So the way that it looks, if I take my eyeball and look at it from this perspective, okay, what do I have? I have my methyl down, like so. And then I see that I'm doing my handlebar trick here. My bromine is there and my hydrogen is there. Where do I want the bromine? I want it where the methyl group is because I want it in the plane. So I want my bromine there. So where does that put everything else? That would mean my hydrogen is there and my methyl is there. Okay? So that means when I take the bromine and put it here, right here, what's going to be the wedge? That's going to be the hydrogen is going to go here. And then this one is going to be my methyl. All right. Now I have not changed the molecule. I'm just rotating around the alpha-beta bond there. Now I've got the molecule in the proper orientation that I can do a E2 mechanism so that I can predict the product. And so if we take an ethoxide or a strong base, it doesn't matter which, we can see that, hey, this will come in, abstract that proton, go like this, and give us our product. So what would our product be? It would be an alkene. Well, we're not going to use dashes here. I have my ethyl on that side, my methyl on that side. And then what do I have here? So that's a wedge, so my hydrogen's there, and my methyl is right there. Okay. And so that would be the product that we would get. And in this particular example, there's only one hydrogen on the beta carbon, so we are only going to get one product. Okay. So I hope you find that helpful, and that's where we'll stop for today.